Welcome to lecture number 5. We started a review of special relativity in the last few lectures. And in this lecture, I want to consider a specific application of special relativity, namely the relativistic time delay. Note that for further use, I will often abbreviate special relativity as SR, whereas GR stands for general relativity. In this lecture, I want to consider the case of muon in Earth's atmosphere. So muon are elementary particles, and these particles are very short-lived. In the Earth, in particular, a particular source of muons comes from cosmic rays. So cosmic rays are very highly energetic particles that come from outer space. They reach Earth's atmosphere and they collide with some atom in the upper atmosphere in altitudes on the order of 30 kilometers. After this collision, we typically get primary particles such as pions, pi minus, pi pluses, and these are unstable as well, so they decay into neutrinos and muons. These muons then sort of have to make it from their decay point all the way down to the Earth, where we have observatories that are able to capture the signals from these muons and basically find, in particular, information about the original cosmic rays. So it so happens that we can calculate the typical altitude in which these muons must first be produced. In particular, the lowest altitude that we get them from the primary cosmic rays is on the order of 10 kilometers. So this is sort of the lowest that we get these muons, and then they have to make it from this 10-kilometer height all the way down to our observatories that are on the ground. So the vector muons are created at an altitude of more or equal to 10 kilometers. We know the muon lifetime. It's about 2 microseconds. We can assume that these muons are very fast. So the fastest they can possibly travel are at the speed of light. So if they travel at the speed of light, we can estimate how far they get during their lifetime before they typically decay. And we come up with a length that they travel before they have to decay, which is equal to their lifetime, 2.2 microseconds times the speed of light, which is approximately 3 times 10 to the 8 meters per second. So if you put this in, we find that they typically would travel a distance of about 660 meters before they actually decay, even if they travel at the speed of light. Now, clearly, the distance that they travel before they decay is much, much less than the altitude in which they are created. So we can ask ourselves the question, how is it possible that we can observe them in observatories on the ground when they are created at a high altitude and basically are that short-lived? We can use our knowledge from special relativity to resolve the apparent puzzle. So let's take 2 coordinate systems. One of them will be the unprimed coordinate system x mu, and that will be the coordinate system of an observatory, which is addressed with respect to the ground level. In addition, we affix a coordinate system x prime to the muons, which are moving at a velocity v dz by dt with respect to the ground level. And I'm assuming that they are moving straight down, so they don't have any x or y velocities, to simplify the math. We know that the relation between the 2 coordinate systems is given by the line elements. So we know that the line elements are invariant in the 2 coordinate systems. If we assume that x and y for these coordinate systems are also the same, we find the relation for the coordinate differences in the unprimed coordinate system for the ds squared and the primed coordinate system for the ds prime squared. In addition, we take the muons to be addressed with respect to their own coordinate system, so they're not moving in their own coordinate system. So we can take dz prime to be 0. So we are left with the relation d minus dt squared plus dz squared is minus dt prime squared. Now we just pull out the factor of dt from the left here to find 1 minus dz squared over dt squared is dt prime squared. Then we recognize the factor dz by dt to be nothing else but the velocity. So we find that this factor here is 1 minus v squared. If you bring it on the other side and take the square root, we find that dt is this gamma factor, which is 1 over the square root of 1 minus v squared times dt prime. What it means is that if we have a time interval on the Muon's clock, let's say 1 microsecond, that 1 microsecond is observed as gamma times 1 microsecond in the observatory clock. Since gamma is bigger than 1, that means that the time in the observatory is longer than the original time in the Muon frame. So the same restated, the time interval on the Muon's clock is observed as a longer time interval on the observer clock. For velocities that are very close to the speed of light, gamma becomes very large, so that difference becomes meaningful. The question is, how large of a gamma factor do we need in order to resolve the puzzle between the finite decay time and the distance that these muons have to travel so that they can be observed on the ground? So we can revert the relation and say gamma has to be the time element dt divided by the time element in the Muon frame dt prime. We know, or we can take the time element in the Muon frame to be the time that it takes for the muon to decay, 2.2 microseconds. If we plug this in here, we find that the only other thing we need is the time that we have to observe these muons, and the time to observe the muons is given by the distance that they have to travel divided by the speed at which they travel, which we can again approximate as the speed of light. So we have this 10 kilometers divided by the speed of light, which is about 3 times 10 to the minus 5 seconds. Plugging in these two numbers into dt and dt prime, we find that we need gamma factors in excess of 15. And if we go back, that means that we need the muons to have velocities larger than 99% of the speed of light in order for them to decay, not decay before they reach the ground observatory. So we found that 1 unit in the Muon's clock is many more time units in the observatory clock. A common way to state this effect is that the moving clock runs slow. This is a special relativity effect. It just says that time elapses slower for moving objects. And that is what I wanted to talk about in this lecture.